Welcome to Unit 2, Lesson 2 on atomic structure. So when we left off, we had been talking about the history of the atom, and we actually went through the discovery of all three of our subatomic particles, protons, neutrons, and electrons. So what we're going to do today is kind of make sense of some of the other aspects of protons, neutrons, and electrons, and how they're related and how we're going to be able to use them in order to figure out some other information. So let's begin by looking at the atom itself. So if you notice, I titled this slide Atomic Structure, and just a reminder that the atom is the smallest particle of an element that retains the chemical properties of that element. So if you go smaller than an atom, if you look at a proton, a neutron, or electron in isolation away from other things, that doesn't give you enough information in order for you to tell what element you're dealing with. So an atom is really the smallest unit that maintains all the aspects of that element. So two things that I want to talk about here. So first of all, the nucleus is a very small region at the center of the atom. So initially discovered by Ernst Rutherford when he did his gold foil experiment. It contains at least one proton, because if you don't have at least one proton, you're not even a hydrogen. So at least one proton and usually one or more neutrons, which are similar in size to protons but have no charge. So that's why when we were looking to figure out what was causing the discrepancy with mass, once we realized that the mass of the electron was negligible, very small, we were able to conclude that there must be that other particle, that neutron. It was very similar in size to a proton, but had no charge. So now let's take a look at this kind of table that summarizes everything for us. So surrounding the nucleus are one or more negatively charged particles known as electrons. So just a reminder, we at first thought they were kind of just haphazardly floating around the nucleus, but then it was the discovery by Bohr that told us that we have energy levels and that these atoms, or excuse me, these electrons are confined to these energy levels. And then obviously Schrodinger took it a little bit further, Heisenberg took it further, and then we came up with our eventual final model, the electron cloud model. So protons, neutrons, and electrons are collectively known as the subatomic particles. So just going across each of these rows, if we look at the electron, this is the symbol that we're going to use for electrons. And then the electron cloud is where they're found. So you saw that picture on the very last slide of the last presentation. They have a -1 charge, and look at their mass. Their mass is so incredibly small compared to the mass of a proton, it's essentially negligible, which means you can ignore it. And if you look at the actual mass in grams, you can kind of get a sense of how incredibly small that is. 9.11 times 10 to the -28 grams. So it's like a 0 with 27 zeros behind the decimal place, and then finally a 9. That's incredibly small. So if we look at a proton, obviously also incredibly small, but still 2,000 times larger than an electron, we use a symbol P positive for protons. They're located in the nucleus, have a +1 charge. And in terms of atomic mass units, we use 1 AMU as the mass of a proton. And then finally, neutrons, no charge, so N with a 0. Nucleus, no charge here, same approximate mass as a proton. And again, also very incredibly small, but still thousands of times bigger than an electron. Okay, let's take a look at our first term here. So we're going to actually be looking at isotopes and ions today. So an isotope is one of 2 or more forms of the same element. So if you think back, what determines the identity of an element is its number of protons. So here we have 3 different atoms. They each have 1 proton. That means they're all hydrogen atoms. They're just different isotopes, different versions of the hydrogen atom. And what makes them different is their numbers of neutrons. So contain equal numbers of protons, but different numbers of neutrons. So here we have no neutrons, just a single proton. Here we have 1 of each, 1 proton, 1 neutron. And then in our third example, we have 1 proton and 2 neutrons. So if we were looking at masses for each of these, this would have an atomic mass of 1 because of the 1 proton. This would have an atomic mass of 2 because of 1 proton and 1 neutron. And finally, our third copy over here would have an atomic mass of 3 because of the 1 proton and 2 neutrons. This format for identifying which nuclide you're talking about, this is the number of protons, or the atomic number that goes on the bottom. Notice that does not change. And then these names were just developed to identify these other isotopes since they are so important in other aspects. So we use the term deuterium to talk about this. Sometimes it's called heavy hydrogen and tritium. And both of these are unstable nuclei, so they're radioactive particles. Okay, let's take a look at our next slide. I'm going to get rid of these two. So first we talked about isotopes. Now I want to talk about allotropes. So they're also different forms, but for a different reason. So allotropes are different forms of the same element. They have different bonding arrangements, and that's really what makes them different from each other, from their other allotropes, between atoms, and different structures with different physical and chemical properties. I don't know about you, but obviously growing up, I never thought about the fact that carbon had so many different forms, and that's just one example. So, believe it or not, the graphite that you use in your pencil, that's carbon. It's the same carbon atoms that make up a diamond, and the same carbon atoms that are left behind when you burn something and there's soot residue. So all of these are different forms of the very same element, and what makes them different is how the carbon atoms are bonded to each other. So we're going to talk about this in a lot more detail when we go on to our unit on bonding. But for now, it's important for you to realize that you could have different forms of the same element, and they have completely different physical properties based on how those atoms are bonded to each other within that one allotrope. Okay, let's move on. So the third and final piece that we're going to talk about today are ions. So as it says up here, ions are atoms, or they could be molecules, which are groups of atoms that are bonded together, in which the total number of electrons is not equal to the total number of protons. That's important. So anytime you have different numbers of protons and neutrons, protons and electrons, you have an ion. So in this case, I'm going to show you some examples down here. Once you have a different number of protons and electrons, you end up with either a positive or a negative charge, depending on what you have more of. So in this case, we have the atom sodium. So sodium, if you look on the periodic table, has 11 protons and 11 electrons. And this is a picture of the atom chlorine. Chlorine, if you look on the periodic table, has 17 protons and 17 electrons. When these two numbers are the same, it's a neutral atom. Same thing over here, neutral atom. However, in this example, sodium is going to give up one of its electrons to chlorine. So this is kind of like a before and after. So before, they have equal numbers of protons and electrons. And over here, they're going to have different numbers. So sodium will still have its 11 protons, but now because it gave up one of its electrons, it winds up having a overall +1 charge. And chlorine still has its 17 protons, but now because it gained an electron, it has 18 electrons. And because it has more electrons than it has protons, it has an overall negative charge. The negative charge means it has more of the things that are negatively charged than it has the things that are positively charged. So this winds up with a -1 charge. Okay, for this next part, we are going to look at an activity called the element inventory. And what we're going to do is we're going to get a sense of exactly how many protons, electrons, and neutrons something has, as well as a couple of different formats for writing this up. It's important that if you do this, you have a copy of your periodic table that you can reference, because otherwise you're not going to be able to figure out the number of protons that you should be writing down. So we're going to start with the first example and the element barium. So if you look for barium on the periodic table, you're going to find it toward the left side of the periodic table, about 3/4 of the way down. So the first one, the first column that we're going to fill in for barium is the symbol for barium. So symbol for barium is going to be Ba. And then if you look up the atomic number for barium, the atomic number for barium is 56. Now, I mentioned this in passing earlier. However, I want to remind everyone that the atomic number determines the identity of the element. That is also equal to the number of protons. So, protons tell you what element you have. No other subatomic particle can tell you that. Once you know the atomic number, you can fill in the number of protons over here. The next part is the hyphen notation. So in the hyphen notation, you simply write the name of the element, hyphen, and then the mass. So in this case, we're going to have barium, hyphen, and then the mass number, which is right here, 137. So hyphen notation is a quick way to identify which isotope of an element you have. Remember, we could have 3, 4, 5 different bariums, all with different masses because they have different numbers of neutrons. Okay, the next thing that we're going to look at is the symbol notation. For the symbol notation, you don't use the element name, you use the element symbol. And then on the top, just like we saw with the hydrogen, deuterium, and tritium example, on the top we're going to have the mass. So it's going to be 137, right, barium here. And then down at the bottom, we're going to have 56. The number of neutrons is going to be equal to the number of protons plus the number of neutrons. So in this case, if I add these two numbers together, I'm going to get 137. So the question then becomes, okay, well, what number of neutrons, when I add it to 56, will end up giving me 137? And the answer to that is 81. So keep in mind, this protons plus neutrons equal the mass number. This chart is designed to force you to go back and forth, back and forth. You can't do it linear. You're not going to be able to go straight across left to right every time. So you really have to think about what information you're presented with and then kind of work your way backwards and forwards. The last part, if you look all the way on the right side, you'll find out that this has a charge of 0, meaning that the number of protons and the number of electrons are equal to each other. So in this case, we can fill out the number of electrons and say this is also 56. Okay, let's take a look at a second example. So if you notice, in the second example, you're not told what element it is, you're not told the atomic number, you're not told the number of protons, so somehow you have to figure out what element this is using other things at your disposal. So what you're going to look at is the charge. So if you notice, the charge is -2. That means you have more electrons than you have protons by 2. Keeping in mind, electrons are the negatively charged particle. So if I have more electrons than I have protons by 2, and the problem tells me that I have 54 electrons, then I must have 52 protons. That's important because once we identify the number of protons, a whole bunch of other things open up to us. So first thing is now I can identify what element I have. So I'll find element number 52 on my periodic table. That's the element tellurium. It has the symbol Te. When you are filling in the column with the symbol, check for a charge. In this case, we have a charge of -2. So up here in the top right of tellurium, I'm going to use the charge to negative to indicate whether or not I have the same number of protons or electrons. So in this case, I have more electrons. Next part, the atomic number, remember, is equal to the number of protons. So in this case, my atomic number is going to be 52. The next part, barium, and then hyphen mass number. Well, I don't know what my mass number is yet. So before I figure out this part, I need to figure out what my mass number is going to be. So I have 2 and 3 is 5. 5 and 7 is 12. So I have a mass of 125. So now I can write tellurium 125. And then finally, with my symbol notation, I have Te. I have, in this case, a charge of -2. Up top, I write my mass. On the bottom, I write my number of protons or my atomic number, same number. Okay, before we go and do a third example, I want to take a minute and show you how this looks like when you're typing it into your document. So I'm going to ask you to open up your document. This is called the element inventory, and we're going to fill in the first parts together. Okay, if you're looking at the element inventory with me, let's go through and fill out what we just completed. So for element symbol, I'm going to put Ba. For the atomic number, I'm going to put 56. Remember, that is also the number of protons, so I can jump over to here and put 56. The next one was the hyphen notation. So I have the element name, barium, plus, or hyphen rather, 137. Now, for the symbol notation, I want you to superscript and subscript the mass and the atomic number. If you do not superscript and subscript the mass and the atomic number, the maximum that you can earn on this assignment will be half credit. So please take the time to listen very carefully to superscript the mass number, subscript the atomic number. There's an easy shortcut for this. So to do a superscript on Google Docs, hold down Control and hit period. That will make the cursor smaller and on the top. And you can type in the 137. To do the subscript, hold down Control and hit the comma. That'll allow you to type in the atomic number, 56. To go back to the regular format, hit Control comma once more. So I can type in Ba and it will be normal size. The next part, we have to fill in the number of neutrons. In this case, the number of neutrons was 81. And because our charge is 0, the number of electrons is 56 as well. Let's go on and look at our second example. So we identified the second example as tellurium. So it has the symbol Te, and the charge on this is going to be 2-. Now, sometimes you'll see it written as -2, but normally when it's attached to a symbol, you write the number first and then the positive or negative second. So in this case, I'm going to hit Control P, 2-, hit Control P again to go back to normal. Tellurium is atomic number 52, as we discovered. So I can fill in the 52 here. And our mass for tellurium, again, is 125. So I can go back and hit tellurium hyphen 125. And finally, superscript, control period, 125, subscript, control comma, and that's going to be 52, and then go back to normal, so hit control comma again, TE, and now to put the charge on, control period, 2-. So to get a subscript on the bottom, like a subway, subscript, we hit Control and then comma. To get a superscript up above the letters, we hit Control and then period. Let's take a look at our next example. So if we look at the periodic table and we find the element with the symbol CD, we'll find that we have cadmium. If you look on the periodic table, you'll find that cadmium is atomic number 48, which means that it has 48 protons. Over on the element symbol part, all the way over here, we saw that it has a 2+ charge. So we can write that as either +2 or 2+ in our last column. If our charge is 2+, that means we have more protons than we have electrons. So if I have 48 protons and I have more than I have electrons, I must have 46 electrons. Next part, we're going to add together our numbers of protons and neutrons. That will add up to be 113. And finally, we can fill out our mass and our hyphen notation here. So there's the hyphen notation, and then our symbol notation is going to be superscript 113, subscript 48, hit Control C again to bring it back to normal, CD, and then superscript one last time to give us the 2+. All right, we will do 2 more examples together. So the next example we have is atomic number 51. If you look on the periodic table, atomic number 51 is the element antimony. Its symbol is going to be SB. And now if I check this last column where the charge is, I'm going to add on that 3 negative charge to my symbol. For my hyphen notation, I can type in, spell correctly, antimony and its mass, which in this case is 120. In my next column, superscript the 120, subscript the 51, hit Control comma again to bring it back to normal, and then lastly superscript the 3- charge. Moving over to the number of protons, I can fill that in. It's the same as the atomic number, 51. The number of neutrons is going to be the mass number, 120, minus the number of protons, 51. So this will be 69 neutrons. And then finally, for the number of electrons, I have a -3 charge. That means I have more electrons than I have protons. So if I find out that I have 51 protons, like I do in this case, that must mean I have 54 electrons. Alrighty. The last problem that we're going to do together is tungsten. So tungsten is kind of tricky because it's represented by a symbol that's nowhere found nowhere in its name. It's represented by the symbol W. It actually comes from wolfram. And we're going to add our charge to that. So it's going to be hold down Control, hit period, type in 6 positive, hold down Control and hit period once more. Now we can move over to the next column. The atomic number, if you look on the periodic table, is 74. So we can drop a 74 in for our number of protons. We have our mass number, so we can type in our hyphen notation rather quickly. Moving on to our symbol notation, we have 184. We're going to drop down to a subscript and type in 74. We're going to bring it back to normal level. We're going to type in W and then superscript the 6 positive that goes on the end. Finally, moving over to the number of neutrons. Remember, neutrons plus protons equal atomic mass. So if I have the mass and the number of protons, I can subtract those two to get 110 110 neutrons. The last column is the number of electrons. So for this one, we compare protons and electrons. The fact that we have a positive 6 charge means we have more protons, positive, we have more protons by 6. So if I have 74 protons, that must mean I need 68 electrons. All right, I would like you to try the remaining examples on your own. If you run into trouble, I am offering office hours. Please check Schoology to see what date and time they are being offered. Also, as part of the office hours this week, I'm going to be going over several additional examples on this homework assignment. If you have questions, please make a point to join the office hours this week. Otherwise, I hope everyone has a great week. I look forward to seeing you at office hours, and please let me know if you have any questions. Thanks, everyone. Bye now.